The law of total probability provides a way to compute the total probability of an event based on conditional probabilities and the probabilities of other related events. It can be used to decompose complicated probability problems into simpler pieces and is often used in conjunction with Bayes' theorem. Mathematically, the law of total probability states that the probability of an event A is the sum of the probabilities of A given each of the mutually exclusive events BE, weighted by the probability of each event BI. Here, P of A is the probability of event A. Sigma is the summation symbol, which means to sum up the terms that follow it. I represents the index of the summation, and n is the total number of mutually exclusive events by. Notice that all the events bi are mutually exclusive, meaning that they cannot occur at the same time. P of a given bi is the probability of event A given that event bi has occurred. Finally, P of bi is the probability of ith event. Let's get an intuition of why the formula for the law of total probability makes sense by visualizing it. Consider a sample space S, which is divided into three mutually exclusive events, B1, B2, and B3. Then we also have event A, which is a subset of the sample space S and spans across all the events B1, B2, and B3. We can represent the span of event A as the union of the events A and B1, A and B2, and A and B3 like this. Because the union of these three intersections is equal to the event A, we can write the probability of event A as the union of all three intersections. If you recall the second axiom of general probability, which we discussed in earlier videos, the probability of the union of mutually exclusive events is the sum of the probabilities of each event. Also, recall the equation of conditional probability, which states that the probability of event A given event B is equal to P of intersection of A and B divided by P of B. Rearranging the equation of conditional probability, we can write the P of the intersection of event A and B as the product of the probability of event A given event B and the probability of event B. Substituting this equation into the law of total probability formula, we get the final formula for the law of total probability. Now that we have an understanding of the law of total probability and Bayes' theorem, let's apply it to a real-world example. Consider a spam filter that classifies incoming emails as spam or non-spam based on the words in the email. In this example, let's say that word free is a common indicator of spam emails. Based on that, let's define the following events. Let A be the event that an email is spam, and let B be the event that an email contains the word free. Note that these events are not independent because the presence of the word free does not guarantee that the email is spam. From the historical data, we know that the prior probability of an email being spam is 0.2. It means that 20% of the emails we received in the past were spam. We are also given that likelihood of word free appearing in an email, given that the email is spam, is 0.8 and 0.1 if the email is not spam. What we are asked to find is if the incoming email is spam or not. To solve this problem, first, we can use the law of total probability to find the total probability of the event B, which is the probability of the word free appearing in an email. Substituting the given values into the formula, we find that the probability of the word free appearing in an email is 0.24. Next, we can use Bayes' theorem to find the probability that an email is spam, given that it contains the word free. Substituting the values into the formula, we find that the probability of an email being spam, given that it contains the word free, is 0.67. By understanding the probabilities of certain keywords appearing in spam and non-spam emails, an email system can classify incoming messages more accurately. That's all for this video. I hope you found it helpful. In the next video, we will look at what dependent and independent events are. Thank you for watching.